Hi children, welcome to Easy Physics. Let us make physics easy. Today I would like to discuss grade 10 physics chapter 13 magnetic effect of electric current. We can start with magnetic effect. Magnetic effect of electric current. In the previous chapter, we have already studied about the heating effect. Mainly, there are three effects of electric current. Alright? There are three effects of electric current. Magnetic effect of electric current, heating effect of electric current, and chemical effect of electric current. In grade 10, we have only heating effect and magnetic effect. Heating effect we already studied in chapter electricity. Okay? Now we have magnetic effect of electric current. What is magnetic effect of electric current? Magnetic effect of electric current means the phenomena of producing a magnetic field around a current carrying conductor when current passing through it. Okay, this is known as magnetic effect of electric current. It was discovered by Hans Christian Easter. Hans Christian Easter. Okay, so the magnetic effect of electric field is magnetic effect of electric current is discovered by Hans Christian Easter. So what he did is during one of his experiments he noticed that compass needle near a current carrying conductor deflected, and he repeated his experiment several times. And finally concluded that a magnetic field is produced around a current carrying conductor, right? So what he did is we can explain this. So consider a circuit consists of a cell and a switch. Okay. Consider a circuit consists of a cell and a switch. Okay. Now keep one compass near. Compass. You know what is compass, right? Compass is that this is compass. Okay. To see the direction of magnetic field, direction and presence of magnetic field, we can find out by using this compass needle. Compass needle itself a magnet, right? Okay. So keep a magnet near this conductor. Okay. Okay. Now what he did is he allowed the current to pass through this circuit. That means close the circuit. That means switch on. Okay. So you can see that the current is passing through it. Right? Then current pass through the circuit. Okay. Now see, you can see that then what happened is this compass needle deflected. Okay. Then he repeated the experiment by reversing the battery. How reversing? By changing the polarity. Okay. So here it is minus, this plus. So current direction also will change, right? Direction of current also will change. Positive to negative. See, like this. Okay. This time he noticed that the deflection of the compass needle is in the opposite direction, right? That means the deflection, that is direction of magnetic field, depends on the direction of electric current. Okay. So finally he concluded that Hans Christian Easter concluded that a magnetic field is produced around a current carrying conductor, right? This is known as magnetic effect of electric current. Magnetic effect of electric current means the phenomena of producing a magnetic field around a current carrying conductor when a current passing through it. Right? Now we have magnetic field. Okay, magnetic field. What is magnetic field? We know field, right? So, for example, during this cricket match, you know, when one team is bowling, other team is standing around the wicket to catch the ball, right? So that is field. Field means the region around that is in the case of cricket, the region around the wicket where the ball expected to come, right? Or ball expected to reach, right? Similarly, the magnetic field means the region around a magnet. The region around a magnet. For example, here it is. See, here this is a magnet, bar magnet, right? No, two poles are there, you know that, north and south. So, see, so two poles are there, right? North and south. So if you keep any magnetic object means like iron or another object near this bar magnet. Okay, for example here. So it may attract or repel, right? So that means a force is exerted here nearby. If you are keeping here, nothing will happen. Okay, so that region around this magnet, the space around the magnet, will exert a magnetic force. That is what is called magnetic field. Here nothing will happen, right? So some region only around the magnet will exert a magnetic force. That is what is called a magnetic field. This we can find out the magnetic field of a bar magnet by using a simple activity. To find out the magnetic field around a bar magnet, let us do an activity. For that, take one white paper, right, and fix it on a board by using thumb pin like this. Okay. Now keep one bar magnet at the center of the white paper, right? Okay, like this. Okay. Now sprinkle iron fillings. This is iron fillings, right? Iron fillings means iron powder. Sprinkle uniformly around the bar magnet like this. Okay. Like this, right? Now just tap the paper like this. Just tap it, okay. Iron fillings are arranged in a definite pattern like this, right? It's a line. Now you can see that. See, iron fillings are arranged in a definite pattern. See that? See it arranged in a definite pattern. So okay. So this here only, this region only, the iron fillings are arranged, right? Why this iron fillings are arranged that region only? Because this magnet influences this iron fillings. Therefore, a magnetic force exerted on it. That is why the iron fillings are arranged in a definite pattern. Okay. So this region only you cannot see here, right? Here also you cannot. Here also you cannot see. See, here you cannot see. Here you cannot see, right? So only the region around this magnet, right? So this region is known as magnetic field. The region around a magnet where exert a magnetic force. If you sprinkle iron filling somewhere else, little far, it will not arrange like this, right? So this is because of the force exerted by the magnet only. Because that region only that exert, right? So this is the magnetic field. Okay. Now we have magnetic field lines. What is magnetic field lines? We know magnetic field. Field means the region around a magnet where exert a magnetic force, right? Then what is magnetic field lines? Magnetic field lines means path around a bar magnet along which north pole of compass needle tends to move, right? North pole of a compass needle tends to move. So the magnetic field lines of a bar magnet we can draw by using a simple activity. Okay. For that, take a white paper, and fix it on a cardboard. Okay, white paper and fix it on a cardboard like this. Okay. Now keep the bar magnet at the center of the white paper. So this is a bar magnet. Bar magnet have you know that two poles, north and south, right? Why came north and south? Because a freely suspended magnet align the geographic north and south direction, right? The end that point towards the north is known as north pole, right? And the end that point towards the south is known as south pole. That we know. Okay. So now keep this bar magnet at the center of this paper, right? Okay. So keep the bar magnet at the center of keep the bar magnet at the center of the sheet, white paper. Now next one is keep the compass. This is a compass needle. Keep the compass needle at the north pole of the magnet. Okay, north pole of the bar magnet, like this. Keep the north pole, right? Now you can see that the south pole of the compass needle point towards the north pole of the bar magnet, right? South pole of the compass needle point towards the north pole of the bar magnet. Okay, and the north pole of the compass needle directed away from the north pole of the bar magnet, right? Because you know that like pole repel each other, unlike pole attract each other. Okay. Now what you have to do is, see, keep like this and put a mark. Okay. Put one mark at the point of that is north pole of this compass needle. Okay. Now move this compass needle and keep the south pole of the south pole of the compass needle occupy the position previously the north pole occupied. Okay. So like this. Point like this. Okay. Now again move it. Keep like this. Okay. So see and mark like this. Then repeat this step. Repeat this procedure step by step till you are reaching the south pole of the bar magnet, like this. Okay. Repeat the same procedure till you reach the south pole. Okay. Now join this point with a sharp curve. Okay. See. And you can repeat the same procedure for getting more lines. Then you will get line like this. Okay. See. So these are the magnetic field lines around a bar magnet. Okay. The pattern. Clear? So these are magnetic field around a bar magnet. Okay. Magnetic field lines around a bar magnet. It's an important question also. Frequently asked question. Draw a magnetic field around a bar magnet. Right? Now what are the properties of magnetic field lines? Okay. Properties of magnetic field lines. Properties of magnetic field lines. Properties of magnetic field lines. First point. So when we are drawing the magnetic field line, we have seen that it starts from north and ends on south. That is the first property. Magnetic field line starts from north pole, right? Starts from north pole and ends on south. And ends on south pole. Okay, so that's first property. Second property is you might have seen that the curve is the lines are continuous, so they are continuous and closed. Okay, or they are closed and continuous. They are closed and continuous. Okay. So then third property is magnetic field lines are closer at the poles. Closer at the poles. Right? That you you might have noticed that when we are drawing the magnetic field lines, at the poles magnetic field lines are closer, right? Magnetic field lines are closer at the poles. Then the fourth one is number of field lines per unit area indicate the strength of the magnet, right? Number of field lines per unit area indicates strength. Okay, number of field lines per unit area indicates the strength of the magnet or strength of the magnetic field, right? So then the last fifth one is two lines of force never intersect. Okay, two lines of force never intersect. Two magnetic field lines never intersect. Why? Two lines of force never intersect. Because if two lines of force intersect each other, at the point of intersection, the compass needle would show two directions, right? So it is impossible. Okay, so these are the properties of the magnetic field lines. Magnetic field lines start from north and ends on south. Second is they are closed and continuous. Okay, then the magnetic field lines are closer at the poles. Then the fourth one is number of magnetic field lines per unit area indicates the strength of the magnetic field, right? And the fifth one is two lines of force never intersect. Okay, so why two lines of never intersect? You know, see, two lines of force never intersect because suppose these are the two lines. See, two lines. Okay, so two lines of force never intersect because at the point of intersection, if you are keeping a compass needle at the point of intersection, if you are keeping a compass needle, the compass needle would show two directions. Is it possible? No. How the compass needle can show the two direction? It is impossible. That is why we can say that compass. That is why we can say that there is two lines of force never intersect. Right? Two lines of force never intersect because at the point of intersection, compass needle would show two direction. It is impossible. Okay. Now we have magnetic field around a straight conductor. To find out the magnetic field around a straight conductor, let us do an activity. For that, let us consider a rectangular cardboard. Now make a small hole at the center of the cardboard. Now pass one thick copper wire through it. Connect the end of the copper wire with the circuit consists of battery, switch, and a rheostat and an ammeter. Okay. Now circuit is open, that is switch off. Okay. Now sprinkle some, that is iron fillings on the cardboard. Okay. Sprinkle some iron fillings on the cardboard. Right. Now switch on the circuit. That means close the circuit. Switch on. Now what will happen? The current pass through it. Right. Now just tap the cardboard like this. Tap the cardboard like this. Then what you can observe that? What do you observe? You can observe that all the fillings are arranged in a definite pattern like this. In a circular pattern. All the iron fillings are arranged in a circular pattern like this. Okay? All iron fillings are arranged in a circular pattern like this. Okay? So why it is arranged like this? This is the field line. What this concentric circular indicates. What this concentric circle indicates, because this is a pattern of magnetic field. This is a pattern of magnetic field around a straight conductor. Right? So magnetic field around a straight conductor carrying current is the concentric circles. Okay, concentric circle. Clear? Now we have seen that a magnetic field is produced around a current carrying conductor. Right? Now how can we find out the direction of this magnetic field? Is there any rule? Yes, we have one rule to find out the magnetic field around a current carrying conductor. That is right hand thumb rule. Right hand thumb rule. Right hand thumb rule. So right hand thumb rule gives the direction of magnetic field around a straight conductor carrying current. Right? So by using right hand thumb rule, we can find out the direction of magnetic field around a straight conductor carrying current. Now how? So suppose this is a conductor carrying current. Now according to right hand thumb rule, okay, right hand thumb rule, imagine hold the conductor in a right hand such that thumb points towards the direction of current. Suppose the current is going upwards. Okay, so thumb points the direction of current. Thumb points in the direction of current. Okay, then the encircling fingers will give the direction of magnetic field. Right? According to right hand thumb rule, imagine hold the conductor in right hand such that thumb points this one. See, so this is a right hand, right? So hold the conductor in right hand such that thumb points in the direction of current. Then the encircling fingers will give the direction of magnetic field. See, encircling fingers. So in the how it is, that is anti-clockwise direction, right? The encircling fingers, this one, encircling fingers will give the direction of magnetic field, right? Like this. See, suppose this is a conductor. See the direction of current. Okay, it's the direction of current. Okay. Now, see, the direction of current is upward. So hold the conductor in a right hand, such that this one, such that see the thumb points in the direction of magnetic field. Then the encircling fingers will give the direction of magnetic field. So in this case, like this, right? Direction of magnetic field. Okay. So that is in the anti-clockwise direction. Okay. Suppose the current direction of current is like this. Okay, this is another case. So imagine hold the conductor in the right hand such that thumb represent the direction of magnetic field. Suppose the direction of current is like this, right? Now imagine hold the conductor in the right hand such that thumb represent the direction of current. Then the encircling fingers will give the direction of magnetic field. See, in this case, like this. That is here it is anti-clockwise direction. Here it is clockwise direction. Okay. So by using right hand thumb rule, we can find out the direction of magnetic field around a conductor carrying current. Right? I hope all of you understand this session. You can download lesson notes through link which is provided in the description box. We can meet in next class. Thank you.